Swayam Prabha. Digital India. Educated India.
We have so far thoroughly discussed the use of isothermal titration calorimetry and differential scanning calorimetry in dealing with the protein folding unfolding or protein ligand binding reactions. And we have discussed in details how recent developments in isothermal titration calorimetry have helped in understanding the binding interactions between a ligand and a protein within a certain affinity range. We also discussed that if the affinity is very high, then one can even use the differential scanning calorimetry to address the binding phenomena and to extract the binding parameters quantitatively. Today, we will discuss the use of titration calorimetry as a tool to determine thermodynamic and kinetic parameters of enzymes. And we will address how the enzyme catalyzed reactions can be studied by using ITC and the kinetic parameters. When we talk about the kinetic parameters, we talk about the rate and we talk about the rate constants. Let us recall one of our earlier discussion when I mentioned that thermodynamics will tell the direction of a spontaneous change. But thermodynamics cannot tell that how much time it will take. That is where the kinetics comes into picture. So, the question is, can isothermal titration calorimetry be used to address the kinetics of a process? The answer is yes, and we will take the example of enzyme catalyzed reactions and demonstrate that today. But before we go into derivation of certain equations, let us discuss a little bit about the enzymes. Let us take a look at the slide. Where are the enzymes used? Let us take a look at the first comment. The use of enzymes in the diagnosis of several diseases is one of the most important benefits which is derived from intensive research in clinical chemistry since 1940s. Abnormal levels of different enzymes in serum have been used to diagnose myocardial infarction, acute pancreatitis, liver diseases and several other processes including cancer. Enzymes are also important targets in drug development for several life threatening diseases such as malaria, cancer, diabetes, heart disease and stroke among many others. Enzymes are also very important in the areas of food, detergent and textile industries. Further, in view of the importance of enzyme in various fields, proper determination of enzyme kinetic parameters can be helpful in both clinical and technological fields. ITC has been used to study enzyme catalyzed reactions since 1950s. I made a comment here that ITC has been used to study the reactions pertaining to enzymes since 1950s. Different types of titration calorimeters were available since then, and with time the technological developments have happened to such a large extent that when we talk about the isothermal titration calorimetry today, we need only very small amount of the samples. Let us take a look at the next comment. Another great advantage of using isothermal titration calorimetry is that neither reactants nor the products need to be optically active. So, therefore, isothermal titration calorimetry offers an important platform, an important methodology even to study the rates of the reaction. Now, let us derive some equations. Suppose that in a reaction the heat produced is Q. Let us do some derivations. In an ITC, what we have here, I will just draw one injection peak, it is power or microcalorie per second or microjoules per second versus time, initial baseline, and then there is a injection and the peak. And we know that this area is Q, the amount of heat absorbed or amount of heat evolved. Now, if I divide Q by the number of moles of the reactant added, then this becomes delta H and the units will be per mole. So, therefore, I can write Q is equal to N times delta H. Now, suppose if my total protein concentration, let us say my total protein concentration is equal to, let me write this as P total, and what are the units of this P total? It is moles per liter. That means, if I want to write in place of N, it will be concentration into the volume. So, in place of N, it will be the concentration of the total product formed into volume into delta H. This is the connection between the heat change or whatever is the heat absorbed or liberated. It is the total concentration of the product form, which is also equal to the total concentration of the enzyme reacted, if it is 1:1 binding, into volume into delta H. Now, let me extend this discussion further. What we have derived is Q is equal to P total into volume into delta H. And now, let me write a derivative, dq by dt will be equal to delta H into volume into dP, how the product is being formed with time, dP by dt. what is this dq by dt? This is the rate of heat flow, which is actually the power. Now, let us take a look at the slide. What I discussed is that Q is n times delta H, and that can be connected to P total into volume into delta H, and then if you take the derivative, what I have is dq by dt is equal to delta H into volume into dp by dt, and I just discussed the derivation of this. Now, if I rearrange this equation, I have dp by dt is equal to dq by dt divided by delta H into V. And dp by dt can be written in the form of rate. So, I write rate is equal to K into dq by dt into 1 over delta H into V. So, therefore, dq by dt dq by dt is equal to rate into delta H into V. Fine. So, what I have is Q is equal to P total into volume into delta H, and from this I get dq by dt is equal to delta H into volume into dp by dt. So, now if I go further and connect this dq by dt will be equal to delta H into volume into dp by dt is equal to, what is dp by dt equal to? If I write dp by dt is equal to, assuming that this is a first order, rate constant into the concentration of the protein or enzyme. So, if I write this is equal to K, and for a first order reaction C is nothing but equal to C0, where is the initial concentration of the protein, exponential minus K times T. Try to understand this step where I am retaining K as K, and instead of C I am writing C0 into exponential minus KT. This is what is expected for a first order reaction and connects the heat flow with delta H, volume and the rate constant. Okay. Now, let us go back to the slide. That is what I just derived, that if the reaction follows first order kinetics, then C0 is the initial concentration of the substrate, and we can come up to this equation. That means, here if I am able to determine dq by dt, I should be able to get the rate constant for the reaction. Now, let us discuss a specific example of Michaelis-Menten kinetics. And what is that? In Michaelis-Menten kinetics, the reaction between enzyme and substrate is described by these two steps, where step 1 is enzyme plus substrate is forming enzyme substrate complex, where the rate constants are K1 and K minus 1, and step 2 is enzyme substrate then decomposes into enzyme plus formation of products, rate constants are K2 and K minus 2. Keep in mind that K minus 2 is much smaller than K2, and it can be, that means the reverse reaction can essentially be ignored and only the forward reaction be considered. If we consider that, then our mathematical treatment will be like this. We have enzyme plus substrate. This will form an enzyme substrate complex, and let the rate constants be K1 and K minus 1. Then this enzyme substrate complex will dissociate into enzyme plus product, and the associated rate constant is K2. Now, if we look at the intermediate in this overall reaction, the intermediate is this enzyme substrate complex. And if we remember steady state approximation, what we used to do in steady state approximation is, since the concentration of the intermediate remains nearly the same for most of the duration of the reaction, the rate of change of concentration of the intermediate with respect to time, we can set it equal to 0. So, that is what we will do over here. We will write d Es over dt, which is, let us take a look at this, K1 Es is being formed. So, I will write K1 into E into S. Now, accounting for the reverse reaction with K minus 1 as the rate constant, for the reverse reaction Es is consumed. So, I will write minus sign minus K minus 1 into Es, and now look at this, here also Es is being consumed. So, minus K2 into Es, and this entire thing I will put equal to 0. That is what I was saying, that since the concentration of Es, which is an intermediate here, will remain nearly the same for most of the duration of the reaction, its rate of change of concentration with respect to time, we can set it equal to 0. Now, from this equation, what I have is, if I take out Es, then within the bracket I have K minus 1 plus K2 equal to K1 into enzyme concentration into substrate concentration. Now, I will make use of another fact that the total enzyme concentration has to be equal to free enzyme concentration plus that of its complexed form with the substrate. I can substitute for E into this, and what I will get is ES into K minus 1 plus K 2 is equal to K 1. Within bracket, instead of E, I will use E total minus ES, this is for E, and then I have left over is S. What we just derived is ES bracket K minus 1 plus K 2 is equal to K 1 E total minus ES, and you have S. ES into K minus 1 plus K 2 is equal to K 1 E total into substrate concentration minus K 1 into ES into substrate concentration. Rearrange ES, then you have, if you bring over to this side, you have substrate concentration into K 1 plus K minus 1 plus K 2, this is equal to K 1 into total enzyme concentration into S. So, therefore, ES is equal to K 1 into total enzyme concentration substrate concentration divided by K 1 S plus K minus 1 plus K 2, which is equal to total enzyme concentration into substrate concentration over concentration of S plus K minus 1 plus K 2 over K 1. I have divided throughout by this. And therefore, rate is equal to rate constant K 2 into concentration of ES, that is from the definition of rate applied to equation 2. So, this is equal to K 2 into total enzyme concentration, total substrate concentration over substrate concentration plus this is Michaelis-Menten constant, this one. Now, let us go back to the slide and take a look at. The rate, which is dP by dt, is V max into concentration of S over Km plus X, where V max I am writing as the product of K2 into total enzyme concentration. Why this is called V max? Because the value is maximum when the substrate is very, very large. at that time Km can be ignored and Ss will cancel and V will be equal to Vmax. Vmax is the maximum velocity at saturating substrate concentration. Km is the value of S at which V is equal to Vmax by 2. This you can judge by doing some little mathematics over here. What we got now is the rate in terms of Vmax, Michaelis-Menten constant, and the substrate concentration. This is how you can pictorially represent, whereas as I discussed earlier, Vmax is actually this rate constant, which is the product, the Vmax is equal to the K cat is equal to Vmax into E total, that is the rate constant. So, you remember that we just derived this equation dP by dt is equal to dq by dt into 1 over delta H into V, and dP by dt we have also just now derived is equal to K cat is the rate constant, which is same as K2 as we discussed earlier, into E total into the concentration of substrate over Km plus S, and now you see dP by dt can be evaluated from dq by dt. If I know dq by dt, delta H and volume, I can then get the values of the rate constant and Michaelis-Menten constant. That is what is commented over here. Km, Vmax and K cat can be subsequently determined from a plot of rate versus the concentration of S. How do you determine the rate? The determination of rate requires determination of this flow of power with respect to time. So, this is how it is determined. When the enzyme is added to a substrate or vice versa, the initial mixing will produce some change in heat, and the heat flow is given by this line dq by dt. After you mix the enzyme with substrate, after the product is formed, the new heat flow is this. After the next injection, the new heat flow is this. This is not the main event for determining the rate. The main event for determining the rate is the heat rate, that is the rate of flow of heat, which is determined after the injection has been made, you see in each case. And if I know the delta H, that is the area under the curve, and then I can easily calculate the rate. Rate is equal to 1 over volume into 1 over delta H into dq by dt, and this is how to determine dq by dt. That is, determine the differential power prior to first injection, determine the baseline differential power after the injection, and as you notice here, there is a drift in the baseline, and the drift in the baseline shifts because of the continuous turnover. Product is being continuously formed. Now, how do you determine enthalpy? You mix enzyme with the substrate or substrate with the enzyme the way you want to design the experiment. And suppose if you are adding substrate to enzyme, you make sure that enzyme is not limited, there is excess of enzyme. So, whatever is the amount of substrate added, it is converted to product. Then the area under the curve after proper dilution corrections can be divided by the number of moles, and that will give you the value of the delta H. As you see, on the average, as long as enzyme is not in the limiting amount, on the average the value is minus 11.36 kilojoules per mole in this specific rate, in this specific example. So, area under the curve divided by number of moles of the substrate added will be equal to delta H. The assumption is all substrate is converted to product, and as I discussed earlier, you have to always apply for the buffer ionization effect, otherwise the result will be erroneous. So, delta H BH corresponds to n times the standard enthalpy of buffer ionization. So, therefore, if I know delta H, if I know the rate of heat flow, I can derive the kinetic parameters associated with the enzyme catalyzed reaction. Once I know the rate constant, then the activation enthalpy and activation entropy of the reaction can be determined from Eyring equation. Let us take a look at what is Eyring equation. This is Eyring equation, where rate constant is connected to Boltzmann constant, temperature, Planck's constant, and the activation enthalpy of reaction and activation entropy of reaction. If you take the logarithm on both sides and rearrange the equation, take logarithm, rearrange, you will get log k by t is equal to minus delta H by RT, delta H of activation, plus log Kb minus delta S of activation by R. So, if you plot log k by t versus 1 by t, the slope and intercept will give you the values of enthalpy of activation and entropy of activation. So, what we discussed in this lecture is that isothermal titration calorimetry is not just important in getting the thermodynamics of the process. It also very accurately and very nicely helps us in addressing the kinetics of the process. We can get the rate constant of the process and we can determine the rates of the reaction. And along with that, these kinetic parameters, we can also determine the activation enthalpy and activation entropy of the reaction, thus demonstrating that isothermal titration calorimetry is also an important tool in addressing the kinetics of the reaction. Thank you very much.